Hey everyone, this is Brian Femiano. I'm a data engineer at Apple, and this is Elixir, the wickedly awesome batch and stream processing language you should have in your toolbox. So what this means, this is going to be just a quick talk. I'm going to show the Elixir programming language. I'm going to show some examples of how my previous team at SiriusXM Pandora used it to um, work on do workflow orchestration, do batch ingest, do stream processing, a lot of the common things that data engineering projects need. I'm going to show all that in some different ways that you may not have seen before. So if anything doesn't make sense, then there might be some new stuff shown, some concepts you may not be that familiar. Reach out to me on LinkedIn if you want to learn more. I'm happy to answer anything and what I can remember. It's been a few months since I worked on this, but they've graciously allowed me to present on it and talk about it. So that's what I'm going to do here today. So what is Elixir? It's a functional language. It's dynamically typed. It's gaining popularity. Um, in terms of what it actually, so it's based on the Erlang virtual machine. It's Beam compatible bytecode. So when you compile your Elixir applications, you're actually building Erlang-VM bytecode that executes on the Beam virtual machine. That means you can leverage a lot of the Erlang tooling. You can build Erlang processes, which is very good for distributed computing. You get a very good ecosystem when you work with it. The whole community, a lot of the tooling built around it is very dev friendly. That's part of why it's gaining popularity. Erlang itself can be difficult to onboard. I found Elixir is very different, so the community is very welcoming, and you still get to use a lot of the you get to leverage a lot of the strengths of the Erlang stack, but when you're using Elixir, so that's a nice property about it. So why would we bring it into a data engineering context? Okay, so the actor model, which anyone familiar with Scala may have heard this term, Akka. So the actor model comes out of the Erlang ecosystem. And Erlang's been around for a while, but it's actually very, very good for distributed communication that's scalable if you want to do those kind of things. And it has a strong immutability model on data that's been loaded. So you can rebind variables, but data that's already been loaded into memory is immutable. So that's nice. The pattern matching is very strong, very well designed in Elixir. That pattern matching comes in handy for analytics. It has strong support for lazy evaluation over data structures. That comes in handy too. The GenServer agent module. So if you want to manage state with functional languages, mutable functional languages can make managing state tricky, but Elixir has some nice baked-in support to make it easier. Error handling, fault tolerance is very strong, very robust. That comes out of the Erlang stack. You get that also in Elixir. And then the Erlang-VM itself is very battle tested over decades, very hard to crash for running applications, which makes it great for constant running applications and distributed applications. So let's go into an example that my previous team worked on, a services architecture. So how did we configure our services? Okay, so we had the concept of a service. A service would span n number of nodes, and we build an Erlang cluster in order to facilitate those nodes. So nodes would be actually deployed on containers. So a given thing with n number of nodes could span n number of containers. It was usually one-to-one container instances. Nodes running the service can spawn n number of processes too. So you have the concept of a service with n number of nodes, and then you have the concept of a node with n number of processes it can launch. And these processes can actually communicate across the container boundaries in a given service. So that's part of the strength. Very lightweight processes, but very easy communication across them. And we use the library. There's an open source tool called Caravan that we use to actually help Elixir processes communicate across containers with Console. Console's an open source lib. So Console is another tool you can use to manage state and things like that, configuration and what have you. So we would use Caravan to actually help some of that, and we made some adjustments to Caravan to work with that. Airflow is so Airflow played a key role in the orchestration part of this. We would actually wire our workloads. We would have Airflow tasks with a very lightweight that would actually send HTTP post signals to these different Erlang processes running as part of the service. So I'll go show visually what that looked like in a second. This means that we could actually wire up our Elixir workloads as lightweight steps in our Airflow DAGs. And so to actually facilitate this, we had Airflow sensors. When we launch a process in Airflow to actually do work on the Elixir service, we'd have a sensor that would poll with HTTP also to see if whether things had succeeded or failed or whether they timed out, which is also a type of failure. And all of this would be communicated back to Airflow, so we could actually have DAG's block on how the microservice was doing. So that's part of, I think, some unique stuff I wanted to show today. So we'll start real simple with the visual. So this is what the services would look like. We'd have a number of containers, right? So we have the concept of a service. Let's just call it service A. Not that creative, but service A running across n number of nodes, right? And so we have a node might be a one-to-one with a container, but then the nodes can spawn arbitrary n number of PIDs themselves. So, and then PIDs can communicate across the containers. So we can do powerful things with this. Let's actually explore. Okay, so we had that. Now we have our scheduled job framework to get back to the Airflow work. This is our lib we had internally to manage jobs. We had reusable code that we could do across different Airflow things for different workloads. What did the scheduled job framework give us? So that this is the smallest I could make the person window. So that word cutoff is Elixir. Scheduled job framework, you might have guessed, was written in Elixir. The whole point of the framework is to handle coordination of jobs across the Erlang nodes in a service, rerunning failed jobs, and also persisting of status logs for the job. It did not handle, this is key, it did not handle actually launching the job itself or the interjob dependencies. So the job, if it had data that depended on another data source, we didn't use the scheduled job stuff for that. So it had no dependency management, which made it a lot less complicated. And so the whole thing, the jobs are designed to be triggered by an HTTP post from an Airflow operator. So the scheduled job framework does not launch jobs directly. You can think of it that way. The post signals would. Any errors, any unchecked exceptions or errors that were thrown as part of the execution stack would be just logged as a failure as part of the scheduled job. And then we have the concept of a coordinator communicating with different local runners across the service. The coordinator interacts with these different local runners to figure out, well, there's only one coordinator, I should say, and then n number of local runners. And then we would use the coordinator to make sure that when we ran a job for a given argument or set of arguments, that we would only run one instance of the job, and we didn't have multiple launched and running and not accounted for. So what did this actually look like visually? Okay, so let's go through it again. We have the concept of the service, service node 1, service node n. These run as an application tree in the Elixir stack. So first, let's look at Airflow would launch the job, which means we'd send an HTTP signal to actually start processing. That would go to the coordinator for the service. And the coordinator knows from the Erlang cluster of PIDs configured that it has all these different local runners and what those PID IDs are. So the coordinator can very easily figure out which local runner is able to run the job instance. And it can assign it one and only one. And then the sensor starts polling that local runner that's running the job for status. Has it succeeded yet? Has it failed? Has it timed out, etc.? And once it finally gets a status from it, it can do done. Local runner set up so that the job execution is paused or blocked for any reason. Eventually it fails with a timeout. That's part of default arg of the scheduled job framework. So how do you actually wire these scheduled jobs? So now we're looking at real Elixir code here. So we define a module, notifications.jobs. This is just arbitrary notifications thing, just for conceptualizing this. So we define a function, job configs. It returns just a dictionary or a map. You could think of it. This is the Elixir notation for a map. That map has a single key called ingest job. So you might have guessed this is just an entry for one job. And then that defines itself a map. It's a key value pair itself for retry policies, how many retries is allowed before it actually fails. And then the default argument. So we have 11 a.m. as the date for the runtime, I guess. So this is how we actually wire it into the application tree. We have the start method, and we launch. You can think of Elixir processes as when we launch an application, we launch a tree of processes linked together by the supervisor. So they're all, any kind of error with one might lead to a shutting down of all of them, just to make things more easy to reason about, easy to operate over. So when we start the supervisor link to our children, we wire the schedule. The scheduled job won't be the only child in practice, but for this illustration, We just have one single child, which is the scheduled job config. And then we set up our job providers. This is part of the framework. So in our previous slide, we had the module that had notifications.jobs, and that defined the jobs config method. So when we have to supply job providers as part of the supervisor tree wiring, we can say this module notifications.jobs. This is one job provider, and then the function job configs is where we get the config for how those jobs are actually implemented. And then the repo is a property we have to supply for it. We give it a handle to our Ecto database module that handles database ops. Ecto is a nice Elixir database lib that helps manage operations to any kind of database you want. Okay, so let's go through an actual case study. How would we use this? Okay, so we talked notifications as an arbitrary. Let's say that we just want to view how certain things, we just want notifications, logs on all of that. How are our notifications actually received? Are people looking at them when we send them out? And let's say that this information is collected back on some cloud provider or something in raw log form, and we want to do some analysis over it. So the rest of this assumes we have those logs in place, we've collected that information. And now we want to get that information, we want to get that structured data into a particular service that might make it available for whatever else we want to do, right? Maybe we want to visualize it or serve it up to other teams that want to analyze it. We want this structured information, we want to get it into the microservice that's responsible for presenting it. So why would we bring it, why would we have the code that does the data ingest directly in the microservice, right? Two main reasons for this that our team felt. One is we had quite a bit of application-specific code for this functionality that we wanted to reuse. It didn't make sense as a lib because it was only really in one place, and we didn't want to break it out into a couple different places just to do ingest separately. And then also, I think more importantly, we wanted to restrict write access to the database for the service that's hosting the data. Write access only to the service, the microservice that handles the API request to it. So this means that we wouldn't have some job running off in a cloud service that could do writes also, and we wouldn't necessarily know like how a write was performed. Every single write, read op from that database was done in the service directly. So that means we wanted to find a way that our microservices could do data ingest directly. And the scheduled job framework facilitates that. So here's a more detailed view of actually, for this particular case study, how the scheduled job framework comes into place. So we have data at rest. Number one, we do an HTTP post. The Airflow job will launch. We would say, we want to start this job for the day. So we do an HTTP post, the coordinator running in the service. The coordinator PID will figure out which local runner should run. So it assigns the job to a local runner PID. The local runner that gets assigned to it will actually spawn a process to do the ingestion work itself for the job, for that instance. So now we have three processes already coordinating here. And now, so those are steps 1, 2, and 3. 4, you can see 4 has A, B, and C that happen sort of concurrently because they're different processes. We want to iterate through the data, the raw data, the ingestion job as chunks. We want to persist those chunks to the database. And also, at the same time, we want the local runner to send status back to the sensor on how it's doing, either success, failed, or pending, so that the Airflow DAG will block and people can visually see, okay, this is not, data ingest is not finished yet for this. Once it's done, once all the chunks are done or failed, we communicate that back to the local runner, and then that's how the final status will be sent out, and we can get a sense of whether it's done. So what does that code actually look like? Okay, for the ingest job itself, there's a lot going on here, so I'll cover and gloss over all of it. Again, ask me questions on LinkedIn if you want to learn more. With timing is a telemetry module. We have telemetry is a stats dlib. We can instrument Elixir processes just to get stats. This particular one is a timing thing. So how long did this take to run when we launch this run method? We give it a inline function, fn forward arrow. This is where the actual chunk work is done. So we get the day arg from the scheduled at argument that's passed in. Let's just assume that's a valid timestamp. And we check it. We have an upstream ready function that for a given day will actually look to make sure that the data is ready. We do this in Airflow too, but we actually do another defensive check just to really make sure that the data is ready. And the ls operator is just a fancy if not. So We raise an exception. We'll throw an error if the data is not ready yet for the day. But if it is, we can go to the next line. The execution will continue. And we call our storage list objects with prefix. So this is sort of a cloud agnostic visual of what's going on here. But in practice, this might be like a cloud provider SDK that we're working with to get an object handle. So a key thing to know here, so we have our data directory for a given day. We have a connection object so it can list it. This object's variable, this structure is not actually materialized yet. It's just a handle to it. So the next line we have the stream objects data. So for a given connection and a handle to those objects as they exist up in the wherever they are. We want to chunk every 1,000, so this is how we'll build our iteration. And then so that we see this pipe operator. This is where we start to get into what makes Elixir, I think, fun to program in. We can chain data, we can chain function calls together to operate over data structures. So the output of stream objects goes to chunk. The output, the map of chunks goes to the map of the stream process where we parse the lines into batch. And then that output collection goes to enum.map where we finally do the persistence. So up until that final enum.map, it's actually just a lazy evaluation where we're doing the chunks. But when we finally do that write batch to DB, that's where it does the recursive calls and actually builds out the chunk of the first 1,000 from the object stream. But it's nice because if we don't do it that way, then we actually materialize the chunks in line while we're processing through it, and it's a little less efficient. This way, it's just saying don't actually build the stream until we need the first 1,000. So stream the object data, chunk it into every 1,000 records. And that raw data, I think in this case, is text form. So that map, where we see function lines, parse lines, that's actually breaking open the 1,000 lines and then doing some work to build, I think, a structured tuple that we can very easily write to the database in the next function. So those chain calls happen over 1,000 line chunks. That's key. And this is for performance reasons. We don't want to do one at a time, right? We also don't want to load everything into memory at once. And then the final line, capture telemetry, is a callback to with timing for other stats that we might want to capture. I can answer any questions about that offline if you have anything. So quick change of pace, that was batch processing. Let's cover a little bit on stream processing. So the same service in practice, it also listens to a couple Kafka topics to get information that's valid for the analysis. You might actually need to store that in its database also. So we use Kafka Ex. It's an open source Elixir client with support for Kafka 0.8 plus. You can check out the README if you want to learn more. Okay, so this is all what you have to do at a high level for setting up Kafka. We're going to add a mix dependency to build. Mix is the go-to build system for Elixir applications. If you start experimenting it, you'll quickly learn that everything's done with mix. And it's a great tool. And we're going to wire up our consumers to the supervisor module so that those will run as processes also. And we want those to be part of the application supervisor tree. And so that was number 3. I just said we're going to wire the consumers into the application supervisor tree. So that's key. And then we're going to define what the different consumer implementations are. So when we say we wire our consumers into the supervisor tree, we have to define what the consumers are going to do. So we actually have to write a module. We have to write a couple different modules if we want for a couple different consumers. But it's not hard in practice at all. And I'm actually able to show a lot of the code that goes into it. So this is some boilerplate. We'll start the supervisor link. Some of this is just code that we need in place to work with the supervisor tree. The init function. So we have the supervisor init, and we're going to build child specs. Application.getEnv. You can think of it, that's reading config from the application, which I don't show here. But for a given app name, we have a config of consumers. And so build child specs is going to take a list of those configs. You can see it on the last line. It's going to make sure it's a list. It does a nice defensive check of the arg to make sure it's a list. And then as a config, so we take configs and we just pipe it in as the first argument to enum.map. I forgot to mention too, when you work with the pipe, you're saying you're taking the arg from the previous line and you're passing it as the first parameter to the function call in the next line. So when you see here this configs pipe forward, that's actually just starting the chain of execution saying send configs to enum.map and call validate. And then on the next line, the output of that, right, the collection of that's going to go into, for this map, this collection called build child spec on each of them. So let's actually go into, we're going to skip over the validate one. So we have build child spec. So let's actually look at what build child spec is. This is where we also check, so we check config to make sure that itself is a list. And we're going to parse out the consumer group args. This is where we actually need to build the consumer config parameters, actually wire into the supervisor tree. So we're going to assume some things are as part of the config, the consumer impl, right, the module name, the group name we want, the topic name it's going to read from. And we pass in, there's URIs and some other, actually get the Kafka host that we need to connect to the topic. And then we return back a dictionary where we have the supervisor name. I guess that's not shown in this function here, but that I think is passed in. Or it might be available as part of the broader module that this is in. I cherry picked this from part of the module, so forgive me for that. Start is the Kafka consumer group with the start link, and we're going to take our consumer group args and send that all to the start as a tuple. And type supervisor, so it's linked back to the supervisor. All of that, and that's in the dictionary, just goes right back to child spec. So jumping back from a slide, that's ultimately each of those gets emitted back to the supervisor init. So that's how we can configure our consumer. But let's actually look at a consumer. So we have our notifications consumer. We just have one in this case. We're going to use Kafka Ex gen consumer. So use is an Elixir operator. We get certain functionality for free that's just kind of injected into this module. You could think of it as inheritance, although it's not quite the same. But alias you can think of in terms of what many of you are probably familiar with as an import, right? We want to actually reference that module, so we alias it right in our class here, or our module. Implementation's true, so this is actually an implementation. That's part of the gen consumer use requirements. And then the handle message set has, so the spec is actually, we don't have time to cover the spec things, but that gives us some type safety on mixed builds. We're actually telling it what types are going to come in as the parameters, and then what's output, what to expect for pattern. So if it doesn't pattern match, we get errors. It's kind of handy. Okay, so handle message set. This is where the meat of our work is done. So we don't have to actually define a lot of the boilerplate for the consumer itself in terms of the topic and what it's listening to. That was already done as part of the config for the consumer on the previous slides. All we have to define is what we want to do with the messages. So messages comes in as a list, and we start the pipe chain. We send that collection to a map enum, or enum.map. And then for each message, that's what that's going to do is for each message, it's going to decode it as an Abra message. And the &1 is a shorthand to first argument without having to actually create a name for it. You can do that anonymously. And we assume that each message has a dot value, right? In the Kafka Ex protocol fetch message module, where we assume that has a structured value of, has a dot value attribute that we can just do reference. So we're taking that and we're decoding that as an Abra message. And so what the output of that enum.map is a list of Abra messages, a collection of Abra messages. And then we pipe that into an ingest messages function, which is not shown here, but is also part of the consumer. So we can very easily persist our messages. We get, in just a few simple lines of code, which I think is great, we can subscribe to the consumer, process messages on the consumer, react to them as they come in, decode them in line with Abra, and then persist in the database and have a very well-defined consumer that manages all that whole process. So I want to thank you all for listening to this talk. Again, any questions, message me on LinkedIn. I'm happy to respond to anything. The Erlang programming language. So here's some links that you might find. If you want to learn more about some of the stuff talked here, that's the landing page for the Erlang programming language. Elixir, which again is built off of the Erlang-VM, compatible with it, is available at elixir-lang.org. And then some of the open source libs that I talked about are available at these URIs. And thank you all very much for listening to this.